Thank you, Bob. Thank you. Thank you for coming to this meeting. The title by you, The Lost Years, What is Architecture? And please, I'm gonna ask to everyone to join me to welcome Bob Robert Martin, better known as Uncle Bob. I'm really honored to receive you here, Bob. Uh, I think probably he doesn't doesn't need introduction, but he has a very long career. He has been a programmer since 1970s, and he is one of the signatories to the of the Agile Manifesto. Uh, in my opinion, one of the brighter minds in software science. And then it's over to you.
Okay. Well, thank you. Appreciate it. And it's good to be here. I hope everybody is doing well. The talk I'm going to do today is called Architecture, the Lost Years. It's an old talk. I've been doing it for, probably a decade now. And it begins this way. My son asked me to review a project that he had written, and he handed it to me, 12, 13 years ago. And I looked at it and I thought, oh, this is a Rails application. It's obviously a Rails application. You can tell that from the directory structure. The directory structure looks like a Rails application. And then it occurred to me, why is it that I know that this is a Rails application and I don't know what the application does? Why is it that the very first thing I see tells me what framework is being used, but does not tell me the purpose of the application? That disturbed me. And it disturbed me because the web is a delivery mechanism. It's an I/O device. It's a detail. It is not an architectural element. It is just a detail about how we get data in and out of our application. And here I'm seeing at the very top levels of this application, a web framework. That bothered me. So I thought about it for a while, and I thought about architecture. What is architecture? And I started looking at some blueprints. Here's the blueprint for a library, the building plan for a library. And as you look at it, you should be able to see that, yes, that's a library. It rather tells you just by looking at it that it's a library. It's got bookshelves and tables and a circulation desk and so forth. And if that one doesn't convince you, well, this one will. That one is a church. The plan of the building, the architecture of the building tells you what the purpose of the building is. And it occurred to me that architecture is not about frameworks. It's not about the web. It's not about databases. Architecture is about the intent of the system. Now, this is actually a very old idea, and it's come through time from a number of sources. One of those sources is this. This is Ivar Jakobsen. Ivar Jakobsen wrote a book in 1992 called Object-Oriented Software Engineering, in which he described a very nice architecture for applications in general. And if you look at the subtitle, you'll see a use case driven approach. His idea was to base this off of use cases. Now, you may remember the mess that occurred in the late 90s and the early 2000s around use cases. All the consultants had to jump in and become very efficient about knowing use cases, and they sort of ruined the idea. But let's go back and see what Jakobsen meant by a use case. This is a very typical use case. It's got a name, create order. It describes some of the data that would be used by this use case, the customer ID, the customer contact information, the shipment destination, and so on. Notice that there's no detail there. That's an important part of a use case. Use cases are very high level. They don't have detail in them. Then as we go down a little bit, you will see the primary course. The primary course is just the set of steps that the system is going to use to execute the use case. And once again, there aren't a lot of details here. It's all very high level. Number one, the order clerk issues the create order command with the above data. Number two, the system validates all the data. I don't tell you how that validation is taking place. That's a detail for later. I just state that it's going to be validated. The system creates the order and determines the order ID. That's probably using a database, but I'm not going to say that here. I want to keep all the details out of here. And in the end, number four, the system delivers the order ID to the clerk, probably on a web page, but I'm not going to say that here. That's the idea behind a use case. A use case is a very high-level description of a function of the system without involving any details. Jakobson told us that you could turn a use case into an object. In an object-oriented language, you could turn it into an object. I call these objects interactors. He called them control objects. I don't like calling them control objects because that gets confused with model view controller. An interactor is an object that implements a use case at a very high level. Then there are entities. Entities are what we call business objects. Entities are the objects that are part of the business in general. For example, in that create order use case, the order would be an entity object. Perhaps a customer would also be an entity object. Entities have application-dependent business rules. And by that, I mean that the entities depend on the application. They are part of the application. The entities are part of the business. They are independent of the details of the application. The entities would be there even if there were no automation. On the other side of the interactor, we have boundary objects. Boundary objects are interfaces, much like Java interfaces or C# interfaces. They provide a way for data to get into the interactor, and they provide a way for data to get out of the interactor. And you can see the two boundary objects to the left here. One of them is used by the interactor. That would be the output boundary. And one of them is inherited by the interactor. That would be the input boundary. And we can put this all together and see how this all flows. So imagine that we have a user down there. And the user is going to use the web, perhaps. It's the delivery mechanism. It might be the web, it might not, but we don't really care. The user is going to enter some data and try to engage a function. And the delivery mechanism, whatever that is, it could be the web, it could be a console, it could be a service-oriented architecture thing, who cares what it is. The delivery mechanism is going to create a request model data structure. This is a raw data structure. It contains all of the data that the user entered, but it does not know about the delivery mechanism. This is if you were writing this in Java, this would be a plain old Java object. If you were writing it in C#, it would be a plain old .NET object. There's no special stuff in this request model. And the request model gets passed through the input boundary and enters the interactor. The interactor now looks at the request model. It knows what the request model wants to do. It enacts the use case, and it does so by telling the entities what to do. So it talks to the business objects. It talks to the entities and tells them what to do based on the data that was in the request model. And then when that is complete, the interactor reverses the flow and extracts the result data from the entities and creates a new data structure called the result model. The result model, once again, is just a plain old data structure. No, it doesn't know anything about the web. It doesn't know anything about any other framework. It's a plain old Java object, a plain old .NET object, nothing fancy in it. All of the elements in the result model are business related. If there's a date, for example, the date would be a date object. If there's money in there, it would be a money object, all related to the business, knowing nothing about the web or whatever device this is going to be output onto. The interactor then passes the request model out through the output boundary to the delivery mechanism, which then formats it in whatever means is necessary, puts it on the screen, and shows it to the user. That is the basic idea behind Jakobson's old use case architecture. It's a very nice, very clean mechanism. Now, can you test that interactor? Of course you can. It's easy to test the interactor. You just hand it the request model and then make sure it hands you back the right response model. Can you test the interactor without the web server running, without any of the frameworks? Of course you can, because they don't depend on the frameworks. You can test that interactor on your laptop while you're in an airplane over the Atlantic without any network connections. You can test that interactor anytime you want. It doesn't depend on anything. Now you ask, what about Model View Controller? Aren't we supposed to all be using Model View Controller? And of course, Model View Controller is a lovely idea. It's a very old idea. It was invented by this guy. His name is Trygve Renskaug. It was invented in the 1980s. Perhaps even in the late 1970s, and was initially invented for the Smalltalk platform, the Smalltalk language and the Smalltalk platform. And the idea behind Model View Controller was very, very simple. The model is the business object in the middle. It knows nothing about how input happens. It knows nothing about how output happens. It just does business rules. That's all it does. The view is this little blue thing up in the corner. It knows how to display the data in the model. And that funny looking arrow there, that's a callback arrow, an observer relationship, a callback arrow. The model calls the view and says, you should display me now because I have changed. At the lower left, we see the controller object. The controller object handles all the input. So it would be the controller object that listens for keyboard strokes or mouse movements or mouse clicks, and then directs those to the model in terms of commands to the model. The model does not know about mouse clicks or keyboard strokes or mouse movements. It accepts model-oriented commands, business commands. So the job of the controller is to take input data and turn it into commands to the model. The job of the view is to display the contents of the model, and the model's job is to enact business rules. That's plain old Model View Controller, very similar to what we were just talking about, except that in the days since Trygve Renskaug came up with the Model View Controller idea, it has been kind of messed up. People have misinterpreted it badly, and they implement it in a web system sort of like this. They might have a bunch of controllers talking to the web framework. The controllers will talk to a whole bunch of business objects. The views will talk to those business objects and try and send the data to the web, and there is no good separation between them. Unfortunately, because of this lack of separation, controller-like behavior gets into the business objects. View-like behavior gets into the business objects, and there is no good separation. Our goal is to separate, and we're going to do that separation this way. Now here's the interactor and the entities and the boundaries again, and this is right at the moment where the interactor has created the response model and is about to send it to the delivery mechanism. Do you see that double black line there? That double black line is very significant. That's an architectural boundary. Notice that all the arrows cross the architectural boundary pointing in the same direction. Notice also that that direction is towards the higher level component. The things on the left, those are low level things that have to do with output. The things on the right, that's high level stuff having to do with use cases and business. We want all those arrows crossing the architectural boundary pointing towards the high level objects. That's called the dependency rule. The dependency rule says that all source code dependencies point across architectural boundaries towards high level elements. Now let's follow the flow here. The interactor is going to take that response model and hand it out through the output boundary to a presenter. Remember what's in that response model. It's all objects. It's all business objects. It's data objects and money objects and other kinds of objects. It all needs to be formatted. The job of the presenter is to take all those objects and turn them into strings for the most part, probably strings. It's going to turn the money into a string with all the right currency and dots and commas and so on. It's going to take the dates and turn them into a string with the right slashes or dashes and with the date, the month and the day in the right order, and however you do it in your locale. It's going to do all of that work, and it will create another data structure called a view model. The view model is a data structure full of strings for the most part, although there might be a few other things in the view model. For example, it could be that money, if it's negative, should be colored red. Well, perhaps in the view model, we would have a little Boolean flag that says, turn this field red. That might be nice. The presenter could set that flag. You might have buttons on the screen, and those buttons might be gray or not gray, depending on whether the button can be pushed. There might be a Boolean in the view model that tells what the state of the button ought to be. All of the interesting decisions about the data being presented are handled by the presenter. The presenter loads all of those decisions into the view model and then hands that to the view. The view's job is very simple. Take the strings and put them on the screen, or take the strings and send them over a socket, or whatever your output is, whatever your output device is, whether it's a screen or a socket or a teletype, or who cares what it is. The job of the view is to take the view model and represent that out on the output device. Because of that, the view is very stupid. And it's so stupid that I have drawn it here as a kind of ghostly object that barely exists. Can you test the presenter? Could you write a unit test for the presenter? Of course you could. You would just give it a response model and see if it produced the right view model. You could test that on your laptop at 30,000 feet over the Atlantic without any kind of IO devices. You could test the presenter easily without any of the frameworks involved. Can you test the view? It's a little harder to test the view, right? Because you might have to look at the screen, but you could hand the view a view model and look at it, and you could see if the screen had the right things populated on it. You would not have to test the view with the whole system involved. You could test the view in isolation. I talk about all this testing stuff because one of the attributes of a good architecture is that its elements are independently testable. We want to be able to test each independent element of our system without having to put the whole system together and test the whole system as a unit. There are times when we like to test the whole system when we're doing system testing, but generally speaking, we want to break the system up into smaller components and test those individual components without all the frameworks and without all the other stuff complicating matters. And this architecture allows us to do that. Let us draw the architecture again, but this time in a different form. Here you see a kind of diagram that shows this architecture. The entities are in the middle. These are the business objects. These are the objects that would exist even if we were not automating. right? So the bank account object, the order object, the customer object, they all exist even if there's no business, even if there's no application. Around the outside of that are the use cases. These are also business rules, but they depend on the application existing. These are the rules that allow a computer to manipulate the entities. Then there are the controllers and the gateways and the presenters around the outside of that. Those are the objects that mediate between the IO devices and the use cases. And then finally, at the blue level, we've got the things that are really low level, the UI, the database, IO devices, the web. That's all low level detail stuff. If you look to the left of those circles, you will see some black arrows. Those black arrows are pointing in the direction of every source code dependency in this system. They all point towards the higher level side. The blue stuff points at the green stuff. The green stuff points at the red stuff. The red stuff points at the yellow stuff. The use cases depend on the entities. The controllers depend on the use cases. The database depends on the gateways and presenters and controllers. That's the dependency rule. That's the way we want that arranged. Data will flow in both directions, but source code dependencies only go in one direction. What's a source code dependency? Well, if you're using Java, that's an import statement. If you're using .NET, it is a using statement. If you are a C or a C++ programmer, it's a pound include statement. It's whatever that source code statement is that mentions the name of another module that you depend upon. That is the source code dependency. Those are the statements, those are the dependencies whose direction we want to control. How do we get data to flow both directions? If you look at the bottom right, you will see a small example of that. The controller talks to the use case through a polymorphic interface. See that use case input port? That is an interface, a Java style interface or a .NET style interface. And therefore the use case interactor receives all that data from the controller through a polymorphic dispatch, through a dispatch of a virtual method or an abstract method. The use case operates, and then it wants to output to the presenter. It sends its data to a polymorphic interface, which the presenter receives. Notice that all of the source code dependencies from the green stuff are pointing to the red things, and yet the data is flowing in both directions. That's called dependency inversion. When the data can flow in both directions, we have a nice dependency inversion, and we are following the dependency rule. There is much more that we could say about this architecture. I've written a book about this architecture. I give lots of talks about this architecture, but for the moment, I see that our half an hour is almost up. Perhaps some of you have some questions. Perhaps there is a way for you to ask those questions. Therefore, I end this talk and turn things back over.
Thank you, Bob. We do have some questions. So we have a question from Ernesto. He's asking how the architecture design is impacted with the current approaches based on APIs, between parentheses, REST, R-E-S-T.
So REST is a very nice way to communicate with a service that is sitting in some remote location. The way I like to deal with that is if I have some software that must communicate to a service using REST, I will have my software communicate to an interface, a polymorphic interface, a Java interface, or a .NET interface, or a C# abstract class, or a Ruby abstract class. It doesn't matter, some polymorphic interface. The implementation of that interface will then take the data that was handed to it and will turn it into a REST command. I don't want the business objects knowing about REST. I want them simply invoking functions, and then something catches those functions, an interface does, and turns them into REST commands that then send it out over a socket to whatever service is out there. I want to be able to take the user of the service and the service itself, and if I have to, I want to be able to put them in the same computer. I want them to run in the same address space, and I want to be able to take the socket out so that they can simply call each other. And then later on, if I want to put that socket back in, I want to be able to place them in separate services and put that socket code back in. And I want that socket code, that REST code, to be independent of the two communicating elements. I want the two communicating elements believing that they are actually communicating directly with each other.
Thank you. The next question is from Laura, and she's asking, what do you think about those projects where whiteboarding is not part of the process, or about those who refuse to draw lines and go straight to the code?
Oh, there's been a controversy about that for years and years and years. People will be in both camps. I happen to like to draw pictures. I will go to a whiteboard and I will draw little pictures of the code. I don't spend a lot of time at that, and I certainly don't publish it in any way. I don't make it some kind of very formal thing, and I don't make it a phase of the process. But there's nothing at all wrong with a group of programmers going to a whiteboard and scribbling some stuff on the board before they start leaping into code. It's a good idea to have a little bit of a roadmap. I have also found that the things that you draw on the whiteboard are almost always wrong. Once you start getting into the code, you will find things that you put on the whiteboard that were not correct. That's not to say that you shouldn't go to the whiteboard. There is value in going to the whiteboard. Just don't trust what you put up there very much.
All right, thank you. So one more question from Tomas. Are there some examples to see how to use clean architecture?
Oh, there are many examples out on the web. There are a number of people who have submitted projects to GitHub and so on, and some of them are demonstrations of clean architecture. Some of them use clean architecture. I put a number of examples in my book, The Clean Architecture. So plenty of examples out there for you to look at. It is a relatively widely used approach.
All right, and one more from Omar about DDD, how we relate it in clean architecture, because I've seen teams put names like infrastructure, aggregators, and other terms like packages. Is that correct?
So domain-driven design, DDD, domain-driven design, lovely idea. Eric Evans wrote the book 20 years ago, great book. Nothing wrong with using the names that you come up with. The whole point of DDD is to create an ubiquitous language of the domain that everybody can use to talk about the project, the programmers and the managers and everybody and the customers. They can all use this same language, this ubiquitous language to talk about the domain. There is no reason at all why you wouldn't use those names in the clean architecture. You could have entities named after domain objects. You could have controllers and use cases named after domain objects. So I strongly recommend that everybody get that book and read it and understand what Eric was talking about, what domain-driven design is, and use those concepts as part of every design and architecture.
Thank you, Bob. And would you say the same, or what are your comments about BDD?
Behavior-driven design is a way of describing the flow of a use case. It is one of the languages that we use to describe use cases. It's a formalization. So given, when, then is a nice formalization of a way to describe a use case. Perfectly valid. It is not the only way to describe use cases, but it's a very good way. And if you are familiar with the ideas of behavior-driven development, it makes perfect sense to use them with this architecture. Behavior-driven development is also a very good way to phrase acceptance level tests, business level tests. And there are languages out there like Cucumber and Gherkin and SpecFlow that will take those behavior-driven development use cases and give you the framework to automate them as acceptance tests.
Thank you. So Hernan, he's asking, what's your opinion about decentralized and distributed architectures, and how does it impact the evolution of software beyond blockchain?
So beyond the blockchain, did we have to throw blockchain in there? All right, so decentralized architectures. I mean, this has been a very old, very long debate, and the pendulum continues to swing back and forth. We've gone from, centralized computers to lots of little mini computers to, the server with lots of web servers, and then the application moves out to the web and the servers are actually tiny. And we just keep on going back and forth. Now it's all microservices, of course. So we go back and forth through this all the time. The reality here is that decentralization is important for a few things, but not for many things. And those few things are things like scalability and security and throughput. Okay? On the other hand, people have tried to make the case that decentralization is a good design technique, a good architectural technique, and there I disagree. I don't think I don't think they're an architectural technique at all. What they are instead is a way to deploy a well-architected system. A well-architected system should be able to be decentralized easily. It should also be able to be centralized easily. The system itself should not care whether it is centralized or decentralized. All of the communication lines should be abstract enough so that you can centralize or decentralize as you need to, as the application grows and as the customer base grows.
All right, well, thank you very much. Can we have one more question?
Of course.
All right, so Andres, he's asking, what do you think about the hexagonal architecture concept? Do you think it is related or similar to clean architecture ideas?
It is very related. The hexagonal architecture, there are at least 4 architectures out there, and they're all trying to say the same thing. The hexagonal architecture is very similar to the clean architecture. James Copleen and Trygve Renskog wrote a book not too long ago where they talk about the DCI architecture. There's the ports and adapters architecture. They're all trying to get at the same idea. And that idea is the separation of central business rules, application independent business rules, then application dependent business rules, then middleware, and then finally IO devices. That's really what all those architectures are trying to get at. The differences between them are cosmetic. The essence is the same.
All right. Well, with that, I don't see any more questions in the chat box, just words of appreciation to you. Everybody's super delighted to have you. And, we really appreciate you being here and sharing all of this with us. So it was a pleasure to meet you, Uncle Bob, and we hope to see you soon.
It's a lot of fun. Thanks so much.
Thank you.
Bye-bye.
Thank you very much. Gracias a todos.
Thanks.